Hello students, in this video I will briefly explain the solar water pumping system. One of the most economical and viable photovoltaic application today is for water pumping in remote areas. Pumping of water for the purpose of drinking or for minor irrigation during the sunshine hours is very successful application for the standalone PV system without any battery storage. For pumping, it appears to be the most suited application for solar PV as water demand increases during the dry days when plenty of the sunshine is available. There would be less need of the water during the rainy season when availability of solar energy is also less due to the clouds. And the simplest PV water pumping system consists of just a PV array attached to a DC pump, and water that is pumped when the sun is out may be used at that time for storage also in the tank for later use. So the disadvantage of the battery storage can be avoided. The result can be a system that combines simplicity, low cost, and reliability. Matching the photovoltaic and pump in such a directly coupled system without any battery storage along with predicting their daily performance is actually quite challenging task, and more complex system may include a battery and the inverter to run a conventional AC pump along with a linear current booster, that is LCB. And it is the same device that we have seen in the chapter of a solar PV system when we have seen the theory of a PV system with a load condition. So a DC motor as a load. So it is the same equipment that converts the power into high current and low voltage so that the motor can get the starting torque which is directly proportional to the current, and current is proportional to the solar radiation. So the example is shown in the first slide, and over here it is the single line diagram of a solar water pumping system uh, in which PV panel is there, DC to DC converter and DC motor is there, where HS is the suction head for the static lift, and HD is called the dynamic head or delivery head. So here are some of the equations that we should know. The total head means height. Total head is HS plus HD, that is suction head plus discharge head, and dynamic head is equal to HS plus HD plus HF, where HF represents the head equivalent to the friction. One more equation is there about the hydraulic power. In this equation, rho represents the water density, G is the gravitational force, H is the dynamic head, and dq by dt is the flow rate or discharge rate. This is the power flow diagram of a water pumping system. So over here the previously used equation can be used for calculation of a hydraulic power. So if you want to design PV system, first of all we need to calculate what is the hydraulic power requirement. So we need to start from the reverse. Once we know the hydraulic power, then we can estimate what should be the power rating of a PV panel. So once pH is known, then the efficiency of the component is also indicated over here, that is pump, motor, and power converter. So the output of the pump is the input of a hydraulic system, output of the motor it is the input to the pump, and power converter output it is the input to the motor, and PV power output will be the input of a power converter. So considering the efficiency of each and every component, finally we can get the equation of the power, PV power, that is pH divided by multiplication of efficiency of power converter, motor, and the pump. So roughly if we calculate, then the final equation says that the PV power is approximately twice to the pH. So whatever hydraulic power is needed, if you want to design a photovoltaic system, then power would be approximately double to the hydraulic energy requirement. So this system does not include any battery backup. So if there is any requirement of a battery to pump the water at a night period, then that should be included over here.